All right, boom. Welcome to Shaders and Beats, episode number 2. Let me just rename this so we can have Shaders and Beats number 2. My name is Antoine once more, and has again, hi, welcome, beautiful humans of the internet, beautiful people of planet Earth. Hope everything is going good on your side. Today we have a better, I think my voice is better now, and the music in the background too. I went to the store and bought a microphone so I can have better voice, because I realized my webcam mic was very just messy. So let's do it. What do we have on the menu today? If you find that my voice is a bit too loud, or just let me know, because I try to balance, and I'm looking to those kind of meter to balance, but what I'm hearing back is not what you hear back in the video, because I'm doing this kind of the sketchy way, I guess. I'm just new to this whole new thing. So yesterday was just a test, and we tested, and we wrote some shaders. As usual, if you are interested, you could just go to the link of the GitHub, and all the code is there. So here's the thing I always recommend you, if you want to explore the thing we are doing, is to open up a ShaderToy account, and from what we are doing in this live stream, just kind of open it and have fun to just tweak around and see why something works or doesn't work. I'm gonna actually put a music that is Creative Commons, because I realize that music Bandcamp, because I realize if you don't put these, YouTube is insanely good to detect things, and they flag your stream. And so soundscape and noise, summer aesthetic, I don't know. I don't want music. I don't really listen to music when I code. I just put a soundtrack. The ambient drones, that sounds good. Oh, maybe this moment where we choose music. That sounds perfectly good for me. As always, it's time to pick your favorite drink, a cup of tea, a little chamomile, a coffee, I don't know. And let's go. So what do we have on the menu today? We are day 2 of our journey, and we have, actually review 2D like we did yesterday, review 2D shaders, basic shaders. After this, we need to, I'm just gonna check if the sound is good. I know I'm kind of obsessed with the sound, but I don't want it to be too there, just a little bit to give because every time I'm recording those sessions, it's late at night and it's before going to bed, so I want to relax myself and relax whoever is listening. Maybe it's gonna turn into an ACMR podcast on shaders talking about the 30 memories. Anyways, let's not go there. Review TD shaders, then we're gonna make vector matte. Oh, and always, oh my god, vector matte. No worries. Actually, everything we need to take a look at is the cross and dot products of 2Vector. It's not gonna be like, don't really bother. If you're struggling with the term mattes, you know what you could do? Just take mattes and wipe it if it's happier for you. We will go deeper in mattes later, would be a pleasure. But for now, I just want to show you what's the difference between the cross and the dot product. And gonna make a little bit more sense when we dive into the other section of the today's video, which is going 3D and ray marching. So we are going to write a ray marcher. This is something, and when I'm saying a ray marcher, you're gonna have the few lines that makes the code, and if you want to jam more, it's up to you after to open and explore things. But write a ray marcher. Before writing a ray marcher, we're going to go through the bad part of, not the bad part, but the less exciting, which is explain the ray marching algorithms. And I'm gonna go a little bit more into this than inside the writing a ray marcher. There's extremely good resources online, but yeah, before going into materials, into lighting and so on, we need to have a basic ray marcher, and we are going to add a simple sphere, okay, and plane. And if we have time, we're gonna compute normals. We're gonna, yeah, and maybe implement a Lambertian lighting model. But this is not sure. This is only if it's not too late, because I'm trying to keep them nice and fun to watch. And I think that 2 hours live stream is not something that really works. Or it works, but I don't know. Prefer to do 2 1-hour streams than 2 hour streams. Anyways, let's do this. Point number 1. Review 2D shaders. It's not really 2D, but let's review what we have done yesterday. So, once again, I'm going to go to the GitHub. I've put it yesterday. Go to repo. Shaders YouTube session. Yesterday we did few things. We review some of the, if you are interested to know what we have done, go back to video number 1. So we review how to query a texture, how to twitch around the UVs, turn the UVs into polar coordinates and make them implement out the color and stuff we output is based on these querying. So not querying, but those UV. So just to show you where we were at, I'm gonna copy paste the number 3 shader, the shader number 3 we had done yesterday. I'm gonna copy paste, and nothing is gonna show. The reason why is because there is no texture assigned. As we saw earlier, like yesterday, you need to assign a texture to make this whole thing works. So now if I hit play, nothing happens, but we could have had another texture, and now actually we have the result of what we went over yesterday that creates this kind of, where, oh no, shader toy is broken. Okay, no, it's not. Yeah, we have these, we were, which one we were, I think we were working with the brick texture yesterday. And it gives us kind of those trippy 2D kind of image. So let me just, and then we plugged in time to our angle through the to the x component of the polar coordinates we had calculate. And this is just review. So we had a time to this plus equal time, I time. And then we saw the thing moving on the screen like this. And if we put it full screen, there we have this kind of trippy. Find it a bit relaxing to watch, but maybe it's not the kind of thing you're into. And then we multiply it, so this way we could have a kind of more drop-down effects. We played around with the output color. Let me just put plus in here, then we rotate. Yeah, anyways, honestly, I think it's just, we went through a lot, not a lot, but some of the basics, really. Nothing too fancy happening here. In 45 minutes, we cover kind of what we needed to know. There's still a problem. It's because this line out here is I need to correct it. Sorry, I won't go right now. But anyways, yeah. Now let's go to 3D. So the first thing, review 2D shaders. I think we did it. We could maybe review real quick the UV things. I know a lot of what we have done was to fuck around with the UV, but I think maybe we could just review UV. So let's define a vectory color and say that it's uv.x. Now we have the uv.x. We start at 0. Remember, we did this, so we have 0, 0 at the center of the screen. And then if I show you the y, we have the y, and if I multiply those two together, uv.x, then we have this kind of thing. And yeah, we went through some of the things. So here's the thing with these shader live streams. I don't want to go too deep into like explaining like the smooth steps and so on. The thing is, there's a lot of resources online. If you are interested to knowing like how what is a frag chord, what high resolution.xy is doing, what is vectory, why sometimes you see vectory RGB and sometimes you see XYZ, which is the same thing at the end of the day. But like my concept here is just to jam some code. So if and to have a creative output. So if you are interested into knowing more of what is going on under the hood, I recommend Googling if you have any questions. Because I'm going to go explaining some stuff, but few things, I mean, not that doesn't... Maybe we can make a live stream that just explains every little operators of HLSL. But let's go back to where we were. Oh, review 2D shaders. I think this is done. Let's put it done. Done. Okay, as you probably hear by this strange accent, English is not my first language. I grew up talking both French and English. From like around 10 years old, I was talking and listening English. But the people who taught me English, they were not coming from an English country. So, well, they were, but with a very strange accent. And the thing is, I'm a Québécois, French-Canadian, Québécois, as we'd say. And we have a very strange accent. And it seems like every one of us, when we talk, we have a different accent. So if sometimes I'm going weird in some terms or pronunciation, blame my background of French-Canadian. Okay, let's go vector. Vector in computer graphics, they go all over the place. I won't go into vectors. There's going to be some good list of resources you could read tomorrow. But for now, I just want to show you the difference between the cross and the dot product. So to show you this, what I'm going to do is I'm going to define, let's open our good old friend Paint. I know some people say, oh, Paint, it's not good. I'm like, no, Paint is awesome. Let's define a first vector that is going to be vector A, and define another vector. Oh, let me rewind. It's not very. Let's put this one in red. Let's define a vector, okay, that points up, and define this vector, and we call it A. So vector A in 3D, they have three components. They have a X, they have a Y, and they have a Z component. Inside those vector, you have values, meaning how some things behave, not like meaning the direction of, meaning, okay, let me rewind. These three components of vector A represent how the vector is pointing, how many hex it goes, how many Y it goes, and how many Z it goes. Let's define a basic 3D Cartesian coordinate here. I'm gonna say shapes and have a line. So let's say we have I'm gonna put X in blue. I'm gonna put blue. Then I'm gonna put in red X or Y, and in green, green. Because I'm okay. Let's make a simple 3D. We're gonna say that we're gonna focus on RGB because we're going to write this whole idea into the shader. So we're gonna say that hex is red, then rouge, vert, green. Green is gonna be the Y. So I'm gonna make another shape, put it in green, and then the Z, blue. So blue is gonna be the Z here. Let's name these axes. Oh, damn, I'm sorry. There's, okay, but this one is Z and it's in blue. And then, okay, now I can go back to my brushes and name all of these. So in red, we have X. In green, we have Y. And in blue, we have Z. Okay. The vector represents how much it points in any kind of direction. So let's say you are looking to, let's say I'm looking to the microphone here. I'm gonna put my, just to see. So let's say we have a point here. We have the 3D coordinate systems here. And I want to start from there, and we could have a vector starting here to there. And because it's gonna be in the Z-axis, we would have 3 meters. I don't know. I'm just kind of explaining. A vector is simply an amount of direction in X, Y, and Z direction. In this case, the vector Z, or the vector A, is pointing all the way up in the Z direction. It is a bit counterintuitive because I have made it red, and in these coordinate system we're making the y-axis is green. So let's define vector A, and the vector A, as you remember, they have X, they have Y, and they have Z component, and they are just floating point numbers. So what I'm gonna do is say that the A dot X is gonna be equals to 0. Why 0? Well, because we want this vector to be pointing only up, only on the Z-axis. And it doesn't really care where we make it start. The vector just represents direction in X, or amount in X, Y, and Z direction. Okay, we don't, because the vector doesn't change. Like if I say to you, walk 2 meters in front of you, like this idea of you are walking 2 meters in front of you, it's not going to be that much related to where you are. You're just going to apply the same thing. So ears in front of you, walk 2 meters. Vectors kind of work the same thing, the same way. You can flip them around, you can put them anywhere, change, and like once the amount of X, Y, and Z of the vector is defined, it doesn't really care where it starts. What you want to know is how much it moved from the starting point. I won't go into vector math this much, but I want to just review a little bit. It's just a little reminder. If you want to skip this part, feel free to go where we start to jam the code. Then on the Y, we're gonna say it's going 1 unit because it's one unit. And on the Z, well, it's going to 0. Let me just take a sip. Then we're going to define. So let's draw this vector. I'm gonna put it in green. It's a bit counterintuitive, but let me put it in, let's say it's in orange here. Vector A is gonna be in orange. So if we draw it on our 3D, here is vector A. Okay. Then I'm going to restart this song because I love it so much. And now we want another vector that do the same thing, but instead of having a y of 1, it has an x of 1. And I'm gonna draw it first in purple. Oops, in purple. And as you can see, the vector here is going 1 unit on the x. So let's draw this vector starting from 0, 0, 0. We're gonna call it vector b. Let's name here vector b in purple. I'm so bad at drawing. I'm so sorry. Then we have x, we have y, we have z. I'm having fun doing this. Then it's gonna go 1 unit on the x-axis, as you can see here. Oops. 1. Oh, okay. Sorry, made an error. 1. 1. 1. I'm just gonna make a straight line for 1, and then 0, 0 on the other. So now we can actually start to write those shaders, write those vectors into shaders. The good things with HLSL or GLSL is that all the vector maths, you know, all the plus, the y, the minus, the multiply, and so on, they're already been kind of, they are into the language, and they're just waiting for us to use them. We could make another video on how actually vector maths work, but I'm not don't think it's gonna be that useful at this point. We're gonna define a new vector tree. It's gonna be A, and our vector A is 0x, 1y, and 0z. So 0, then we say 1 and 0. Then we are going to define the vector b, and vector b is 1 on the x and 0 on all the others. So to show you the value, we could cast here, or actually we could say that color is equal to A. Now you see A is Y up, meaning it's all green because we just output the color. Then if we put B, it's gonna be all red. And if we put, let's go. What do we want to do at this point? I'm getting a bit lost, so let's get back to cross and dot. Let's make the cross product first. Okay, let's define these two vectors, and let's say you want to say you have vector A here and you have vector B here, and you would want to find a vector, and this is x, this is 1. Okay, never mind, let's rewind. Okay, let's say you have those two vectors and you want to find, so they are like this, and you want to find a vector that is perpendicular to both. So the perpendicular means that the x vector and the A vector and B vector, they are 90 degrees different. They are very like this. And you want to take the cross product, and the cross product is going to return you a vector that is perpendicular to both. So let's define a vector C, and C is gonna be in blue. So C will have an X, a Y, and a Z component, and you kind of see where it gets right now. If we take the cross of, and I'm going very HLSL, not Matty. If we take the cross product of A and B, let me put this one in. Okay, it's going to give us a vector that is perpendicular to both. And because they are only one up on Y, as you see here, and one on the X, if we cross them, it's going to give us 1 on the Z. and this is going to be 0. Okay, let's implement this. So what I'm going to do is say, I'm going to define a new vectory. I'm going to call it C, and I'm going to say cross of A and B. And if I say that the color is equal to C, now we have, okay, here's an interesting thing. Now, because we start on the Y and not the X, it gives us this kind of Z plus from the screen to us. So it gives us this actually. So it's giving us this vector here. This is the Z, but we are in Z plus, and here we are in Z minus. So one way you can kind of fix it around is to switch. So let's you could do the cross of B and A, and that gives you kind of the reverse. So now this means that this vector we had here, forget it, is now in Z plus. And as you see, it's all blue, meaning it's Z plus, it's Z1. We have it here. Okay. Let's see, how long have we been doing this? Oh, 26 minutes. Going slow, but I'm gonna switch the song. Now, so we review kind of the cross product. So it gives you a vector that is perpendicular to both vector you feed it. In somehow very simple terms. So now we're going to see the other one, which is the dot product. And the dot product is taking two vectors but returns a float and not a vector tree. So let me just create a new one and say, if we have vector A going this way all the way up, so just y1, and then we have another vector that is vector B, and it's going x1. If we take the dot product of this guy, let's say they are at 90 degrees. So if we take the dot of A and B, it's going to equal 0. Let me just show you. So if I go, it returns a float. It does not return a cross. It returns a cross. It returns a float. So I'm going to say dot product of, let's say, vector A and B. So vector A is y up, and vector B is all the way x1. So they are perpendicular. So if we take the dot product of those two guys, it's going, and we plug it into the color just to show you. So let's give it the value of RJB of the, because if you remember from last session, if we say vectory and we pass it to dot product, then it's doing this. Okay. So the way the dot product works is, if you take, basically what I do here is I assign, just a little reminder, if you pass a float to a vectory, the constructor is going to assign R, J, and B to the values of what you pass it here. So it's basically the same thing as saying, what I'm doing here is the same thing as saying call, I could probably comment, just a little review, call.r equal dot product, call.jb, and so on. Okay, it's the same thing, but it's easier to do it like this. So now our two vectors, they are completely, they are at 90 degrees, meaning that the dot product is 0. And it works because now the dot product is all black, it's 0. If we reduce a little bit the amount between them. Let's say we make them the boat. Okay, let's say we make both those vector. So we have A, and instead of having B here, let me just remove B that we had here. Let's say we put B to be the same pointing. It's gonna be the same, pointing in the same direction of A. So I could go B, oops, brushes, go B, and say now that we have vector B that is like this. Now, okay, imagine they are the same length. I am sorry. Okay, now let's imagine we have vector B that is, yeah, pointing like this. If we take the dot of A and B, I'm gonna remove this guy, the old B, bye-bye. Bye-bye, my cowboy. Now if we, let's make this, and now the new B is not gonna be pointing 1 on the X, it's gonna be pointing 1 on the Y only. And now that you see, it simply represents that this it returns 1 if the two vectors are parallel or pointing in the same amount, the same direction actually. So if I take B and I make it point, let me, yeah, we could rotate them. So what about if we, so 0, let's say we make 0.5 on here. Then it's gonna return kind of a gray because they're not parallels. So it was a very short review of this. I'm sorry if it was not clear. What I'm gonna do is, yeah, just remember, if the two here's the disclaimer, the cross product returns like in short terms. Let me put the code on GitHub first, so this way you can have fun and implement it yourself. So I could go shader number 4. Okay, and let little disclaimer, commit changes. I love how the new GitHub website, it's been a lot of time since I've used it, and now it seems like you don't even need to have it locally. Yeah, you need, but for simple stuff like this, just works fine. So, short reminder, cross product between two vectors returns you a vector that is perpendicular to both. If we took, in this case, in our shader, we took B and A, it returns us one on the Z axis, so vector C. Then dot product takes two vectors in but returns a float, and the dot product is it's operate on how those two vectors, you feed them, differs in angle. If the two vectors are perpendicular, the dot product is going to be 0. If they are parallels or they have same values on X, Y, and Z, they're going to be returning 1, as we saw. Okay. This is done. I'm sorry. Problem with my English. Going 3D and ray marching. Explain the ray marching algorithms. That is the next thing we have in store. So ray marching. Okay, let's do this. I want to make a ray marcher. Now I'm gonna check out. Okay, just 31 minutes, 33. It's okay. We can definitely make it 1 hour. You know what? I'm gonna take just a little pause, and then going back, and then then we're back. So time to take a deep breath, and just before diving into ray marching, because I need to go to take some of the notes I took during the day because I was thinking about this. So yeah. See you in few seconds. Now I'm fading away. All right, and we are live for part 2. We're going 3D now, so hope everyone is ready to go 3D. It was the most boring break ever. Like, I could have made some animations. Maybe I'm gonna make some. But yeah, I love to just display, just nerdy enough, display a break. Okay, let's go back. So we review these are done, and now we're going into the nice stuff, going 3D and remarching, because I guess it's easy to learn the basic of pixel shaders, but when you open ShaderToy, you're like, how did they make this look 3D? Because remember, at the end of the day, as we saw yesterday, we work at the end of the rendering pipeline. We work after the rasterizer and so on. So we don't have these same fancy things we have in Unity. So, okay. So ray marching, it's a big topic. I won't, so like ray marching is just a family of algorithms. There's ray tracing, there's path tracing, which is a flavor of ray tracing. There's rasterization, there's a lot, like for decades now. Older guys that were born before my parents even were thinking about having a kid, they implemented a lot of ways to display things on the screen. And back in the days, the hardware was not what we have today. Nowadays we have big machine with big GPU with a lot of transistors processing a lot of data every seconds, and we can come to typing shadertoy.com and just create a new shader and we are ready to jam. That was not what it was back in the days. I was not there. Maybe you were, maybe you weren't, but yeah. I'm just gonna drop the volume a little bit because I feel it's a bit annoying. And okay. So now let me just take a look if the YouTube stream is good. It seems it's cool. Perfect. So we're going to go to 3D now, and we're going to take a look at ray marching. And ray marching is a big subject, as I mentioned. So, but the core concept is somehow very simple. Let's say you are looking to where you are sitting right now. Maybe you're in your bedroom, maybe you're at your office, maybe you're anywhere you are, okay? This here is you. This little red point, it's your position. And let's say you look at where you are to like a top-bottom views, okay? So let's imagine there's a camera in the top of the sky right now that is just looking at you. And you have a world, right? So here I'm in my office. It's my house. I'm wearing my house. It's not a house. It's apartment. But yeah. So I'm like on the 4th floor, and there's like a window on the left of me. There's like this desk back. There's like the world around me is composed of things. When we do ray marching, we want to find where things appear in the 3D world. So let's say for now, remove tonight, and sometimes I do this exercise and it helps me a lot understanding ray marching. Like, let's just close your eyes for a second and imagine you are the only person in this black world. There's nothing around you, and you're just here at 0, 0 in red. Then eventually there's maybe gonna be a sphere somewhere. Okay, let's define a sphere. So here's the sphere. Then maybe a bit later there's gonna be a cube. Okay, coming in, and now we're in 2D, but you can easily expand this concept into 3D. But now there is the x-axis. Let me put it in red. There's the x and there's the y in yellow. It's not good. Put it in green because we see it better in green. Now, let's say that you want to move in this 3D world or 2D world. You will walk. You know where. So let's say you want to get to the sphere. So because you see the sphere, your brain is simply going to get, okay, we're going to go to the sphere. But let's imagine a world where there's no such thing as defining things. Like, you cannot see the world. You need to ask the question in reverse. Where are the things to be shown in 3D? Once you know where they are, you can go to them, play with them, interact with them. But for now, we are at this point where what we see is a black, empty void. And we need to find a way to actually reach this this thing. So it's where ray marching comes very, very, very useful. Let's say you have this guy here and this guy here. Ray marching algorithm, it's going to say, okay, let's define a first use case. Let's say you walk in this direction, okay, to infinity and beyond. Okay. You have in ray marching this thing that we called the distance estimator. So it has a lot of name, but in very short concept, what it says, it takes a position as you are right here, and it gives you the closest position you are near. Okay, so it takes the position you are in here, then you query the distance estimation, so let's call it DE, and it returns from this point what is the closest object you are from in these 3D, or in this case, the 2D world. So, but it takes the direction, never forget, it takes where you are going in 3D. And it query 3D space, and it's gonna query like this whole world we define here. It's gonna query this whole world, and it's gonna say, okay, what is the closest object am I from? My red point here, okay? I want to know how far can I walk along the ray, along my direction, because I'm going in this direction. I'm not going to change direction. There's algorithm that's going to implement them, but we won't go there. For now, you have two things. You have your position and you have where you walk to. And the only thing you have to detect if you hit something is this distance estimation, which is going to take your position and query the 3D world, and it's going to return the nearest object. In this case, it's going to be this sphere here. That is, yeah, we trace. The reason why we call it sphere tracing is because we trace the sphere from this point. And we know that querying this guy, it gives us a distance. So we know that and now we are going to go and to walk towards the ray. And now you are sitting here. And now you do it again. You kind of query, how close am I from the nearest object in the scene? And you do the same thing. So you remember, you walk into this direction. The direction does not change. What you do is you query back the DE, distance estimator, and it's going to return where you are from the nearest object. And the nearest object in this case is still going to be the sphere. So there. And you do the same thing. You trace a sphere around. And then, yeah, you kind of get the idea. You query this distance estimation, and from what it returns to you, which is a distance, you just walk towards the ray. In this case, our sad, lonely guy is going to walk and never hit anything. So we're going to use the far clipping plane to be, not far clipping plane, but say, okay, at a certain point, you just get back. You know, like you don't want to walk to infinity. Let me just make a 2-minute explanation, even simpler. So you are here, you have, I'm gonna put it a bit bigger. You have street A and street B. And here is your house. Okay, example, you live on a corner of 2 streets. And here somewhere is a grocery store. Let's say G, it has a position. Okay, it's the same thing as saying, okay, what I have in what I can do is go into a certain direction. Like I could go this way, 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 whatever. You want to reach to the closest thing, right? You don't know where you're going to go, but you want to know, am I going to Am I going to end up at the grocery? Am I going to, let's define another thing. Let's say, here is a bar. Here is the B bar. I'm gonna go grocery, just gross like this. Okay. So what you feed the algorithm is an initial position, which is your house and where you're going in orange. In this case, you're going this way. And the only way you can walk in space is by asking this distance. So it maps where you are here at 0, 0, and it returns the closest object in 3D space, in this case being the groceries. But you continue to walk, you ignore direction. Of course, we are humans. Like in real life, if we go, return me where it's the nearest thing am I, and it's like groceries, yes, for sure, you're not gonna walk through infinity and then go back to your house and start another one and do the same thing. Like you want to go to the grocery, so you just query grocery. But that doesn't work like this in array marching. So yeah, you kind of get the idea. I'm not, we use distance estimation to returns where we are. So, 46 minutes, 10 minutes. Yeah, I think it's, yeah. Okay, now it's time to map into code. And I'm gonna go through my other shaders because I already implemented a lot of time. If you are on a low computer and you open a new tab with shader toys and it's trying to load everything, you're gonna have a Chrome error, as it's happening right here in line. So, oh no, that's not what I want. That was a nice shader though. I made earlier today basic ray marcher, bubbly shades I called it. So yeah, I'm just gonna, I'm gonna copy this guy because it's always come easier when we have kind of references. So okay, we have UV. Let's go back. Let's put on our okay, you know what? Let's remove everything and just say we have a out color that we're gonna say it's gonna be all white for now. So 1, and let's remove everything. So we start from a fresh shader toy. As always, the code is available on the GitHub. You can go there and have fun and implement your own flavor. Now, how the algorithm actually works. So we need a position. Remember, we start here, right? Then what we want to know is we have a 3D space. 3D, let's do line. So we have X, Y, and Z. And what we want to define is this kind of viewer position. Where do we start to send those direction, those rays to intercept object? So you can start by putting it at 0, 0. Actually, it's gonna be ray. Some people call it ray origin. I'm gonna say RO for now, for ray origin, and define a vector tree, and we're gonna say 0, 0, 0. Okay. And basically, if I'm gonna open Blender just to make it as, maybe you will have a better maybe a better understanding on how the algorithm works. If I go to Blender and I put a camera, let's put every rotation to 0. Oh, here is like the viewer space. So the camera is at 0, 0, 0 world space. For now, it's looking down on the Z in Blender, so you would want to rotate, but yeah, it's another way to twist it around. What we're gonna do is gonna say we're going to send rays from camera in Z+, as we saw earlier. So let me it's gonna be sitting on 0, 0, 0. Then, as we mentioned, we have this. So let's zoom in a little bit. So we have your you guy here, and then you send a bunch of rays in 3D into an image that's gonna be defined like this. So you send bunch and bunch and bunch and bunch and bunch of rays. Basically, you send a ray for every pixels. That's how simple it is. You send one ray per pixels. And because our shader runs every pixels, it becomes very easy to implement these kind of things. So we're gonna define the direction, because we want to know where do we send ray to. Okay. So because we have UV, remember we have the U and we have V, and we have the viewer. Let me create a new one here. Then we have our canvas in blue, and this is the UV. So what we want to do is basically send a ray for every. So the direction, the vector is going to be 0, 0. On the U, 0 on the like 1U, 0V, and so on. And we want to change the position of the ray based on the UV. The big question is, how do we actually send in the Z? Because we don't have Z at this moment. The good answer is very simple. So let's define a vector. I'm gonna call it ray RD for ray direction. I'm gonna normalize this guy and say it takes the uv.x, uv.y, and it takes 1 plus. So Z is +1. So it looks in front. Okay. Normalize it. Cannot convert from const medium. Why? I think I need to throw a factory here. That is probably going to work just fine. Yeah. So now we could show RD, and you see that the Z is always kind of pointing in towards the center. If I show ray origin, we start at 0, 0. It's not going to be that useful for now, but I could go RD.x. Now we see where it goes in direction. Y, same thing. Nothing really fancy here. I'm just going to leave to RD, actually. Now, okay. So, now we have let me picture. Now we have your point, which is at 0, 0. This is RO. Then we have RD, which is a normalized vector. This is RD. that points in Z depth, it points in Z plus, but it changed towards the UV. So yeah, for every pixels we have a new ray pointing to try to hit things. Then the next thing we want to do is to we need to make we need to actually increment a word array. So one simple thing is to, and I love this song so much. Okay. So now it's cool. We have array origin, we have array direction, but we need to walk toward this array to actually make, to be able to explain what we saw a bit earlier. Do I still? No, I don't have it. So we have the array, but we want to kind of walk around it. So I'm going to make it in the main image, and I'm going to go int I is equal to 0. I'm going to say hi 128 I++. So that means in here, we're going to query 128 times this distance estimation we saw. You know, we're gonna query space. Where am I? Am I close to an object? Where am I? Am I close to an object? Where am I? And we're gonna go, so like we're gonna walk toward the array until we hit an object. What we need to do at this point is to define a new position that is going to be vectory, because now it's cool. We can walk toward the array 128 times by querying the DE, distance estimation, but we do not keep track of where we are. So let's create a new vec p, call it p, position, current ray pos, I guess, if it makes sense. Maybe I'm going a bit fast in here. Maybe I'm not going that clear, I have to say. And we're gonna say 0, 0, 0. I'm gonna move it away of the scope. We don't need to declare every iteration. We just need to reassign. Now, yeah, we. What do we do? What did I do? Position plus D. Okay, now we need the distance, the holy grail, the map function, or the distance estimation. So I'm gonna call it. I'm gonna make a function called how close am I from the nearest object in scene. Okay, I know it's very ugly, but it makes sense. And this guy here, it's only gonna take a position. It's gonna take a pos, and it's gonna return something. It's gonna return the answer of how close am I from the nearest object in scene. For now, we're gonna affect 1, because we need to go one step higher, and it's to how do we collide with 3D object. So but now if I take now I want to define actually a distance. That was not a good one. So what I'm gonna say is inside the walk along the array, remember here I'm gonna comment, but here we are walking along the array, and I can say we have distance. We can go distance, float distance. Oh, distance doesn't work. Let's say underscore distance. Does this work? And it's gonna be equal to how close am I from the nearest object in the scene. And it's gonna take a position. Just gonna, where's pause? Distance, float. What did I do here? Pause. Oh, yeah, because it's origin. Oh, it's RD. Sorry. Yeah, tricky things here. It's actually hardy. Ray or RO, R origin. but then we need to modify how we walk along the array, and the best way to do this is to use this brand old function p of t is equal ro plus rd times t, meaning that we have where are we on the array? Well, we pass it a t, and it's make this function here, and it gives us from array like here, okay, returns where we are on the array. So based on this thing, so now because now we have the distance. So I'll close mi from the nearest object in the scene. We pass it the array origin. It returns the t, so we could just apply this ro plus rt times t to yeah, we can simply change the distance based on this. So I'm gonna go distance is equal to ray origin times ray direction or plus r direction times t. What is t here? Plus the... Oh, yeah, no, sorry. I'm getting a bit tired. It's getting almost midnight, so... RO, RT times D, yeah, there we go. Should... D, RD, ray direction... What? Oh, no, it's RD. Sorry, damn. RD plus R direction times distance. Is that it? Yeah, distance. Oh, distance. Not here. There we go. Yeah, it's always longer, I have to say. I wanted to go for 1 hour, but now seems like we're at already 1 hour. So. Oh. But let's go. Let's take maybe another little break, and yeah. Be back in 30 seconds. Just need to go take some water. Okay, hello. Let me just stop the music. I'm so sorry. I just realized that my mic was not opened through this whole time. I'm so sorry. Okay, so okay, I don't want to head it because it's part of the live experiment. My mic was closed when we wrote the Ray Marcher. So, but I guess I'm getting tired. So here's the thing. Tomorrow we're going to review some of SDF, some of Ray Marching, what we have saw. Now you can go to sleep tomorrow in the day on your shift of work, kind of, or during your lunchtime, have a bit of like querying your mind on how things work. And tomorrow night we're going to do the next part, which is going to be a very kind, we're going to have the kind of very leaner place where we could start to implement Ray Marching. I honestly thought it would be quicker, but now my mic has stopped working, so I guess it's just part of like now is going to how do we combine, how do we move things, how do we create colors and procedural material-ish. So I guess let's stop it right now. I am so sorry. I'm going to review my sound settings because it's crazy. I cannot believe I'm, like, the thing is I'm hearing back, here's the thing. I'm hearing back myself when I talk because, as I mentioned in the beginning, I am not hearing what you hear on the final hands. So because I was hearing myself, I was like, because the mic is kind of plugged into my headphones and I could just stream. Yeah, I was just kind of wondering. Yeah, I was like taking for granted that you were hearing. Sorry, epic fail. I won't cut it though, because I think because it's a live journey and we're building this thing together, I don't really see why we should cut it. Anyways, thanks a lot for watching in live or later, and have a good night. See you tomorrow for part number 3, where we go a bit deeper into Ray Marching.